Our next presenters are Spela Poklukar and Brasanac. They are data discipline lead and ML consultant at data scientists in Endava. They will introduce Retrieval Augmented Generation, a technology that merges semantic search with LLM-based text generation to enhance accuracy and reliability in responses. The talk will cover the fundamentals of RAG and semantic search, along with an overview of available libraries and vector databases. So Spela and Thea, please welcome to the stage.
Hi, everyone. Thank you for joining us. We're going to explore the topic of Retrieval Augmented Generation. This is my colleague Thea Brasanac. My name is Spela Poklukar. We're data scientists at Endava. We have been working in the past year and a half or so on generative AI solutions, ranging from developing coding assistants, retrieval augmented generation, and AI agent applications, and also fine-tuning large language models to Slovene language. The agenda for today is as follows. First, we're going to give some motivation. Why do we want to use retrieval augmented generation? Then we're going to introduce the concept itself. And then we're going to extend this concept with another concept, AI agents. And then in the end, we're going to show you a little demo that we built that actually demonstrates how both concepts work in practice. So let's start with some challenges of large language models. The very obvious ones are hallucinations. So this is generation of false facts by the large language models and presenting these false facts as they were true. Hallucination is actually something that's inherent to large language models because they were actually trained in a way that they kind of complete the given prompt with the next word that seems the most probable given the context, the prompt that we've provided. So this appears to be something that we're just going to have to live with for some time until we can find a better solution. And then the other challenge that we're going to address today is large language models not having the access to the up-to-date information. So they do have access to some information through their weights. So this is called their parametric knowledge. But this is very tied to the training set, which might contain some factually incorrect information. And also this data set was cut off at a certain time before the training, so we don't have the up-to-date information. So in essence, large language models are primarily text generation tools, and they should not be used as the knowledge bases. But is there something that we can do to address this issue? It turns out that we can, and this is the concept of retrieval augmented generation. So now let's imagine a situation that we ask the question to the large language model. So for example, what's the biggest festival around this year? So if we don't provide any additional information, the model might say, oh, I don't have this information because it's in this year, or it might just hallucinate something, just make up something, a non-existing festival or whatever. But now let's imagine, what if we ask the same question to the large language model, and then we go into some sort of curated knowledge base, into some reliable data source, and we extract the information that's relevant to our questions, for example, information about world festivals. We provide that information to the prompt, as we can see here, and we actually don't ask an open-ended question, what are the biggest festivals, but we say, can you extract the answer to this question from the data source that I've provided? So what happens if we do it like this? Basically, the answer that's actually taken from the source that we've provided suddenly becomes way more statistically probable than the hallucinated answer. So this is a very effective way. How can we limit hallucination? But at the same time, we also connect the large language model to a curated domain-specific up-to-date knowledge. And this is actually the main idea behind Retrieval Augmented Generation, which effectively combines, which effectively connects our large language model to a curated data source that we trust. So now let's explore how this concept, how it works. How do we do that? First, what we need to do is we need to create this knowledge base. So we have a bunch of documents. So this is usually some unstructured text, and we have to encode it. We have to embed it in the vector space. We're going to talk about that a little bit later. So actually encoding this text to the vector space allows the search. So in this way, we build the knowledge base. Let's skip this part for a moment. But then on the other hand, we have our user that asks certain questions, say about the festivals or carnivals around the world. So once the user asks the question, we go to our knowledge base and we search for the entries, for the documents that seem most similar given to the user query. Then once we extract the relevant content from our knowledge base, we combine it in the prompt, as we seen on the previous slide, and give this prompt combined with the content that we retrieved from the database to the large language model, which is then able to extract very nice, curated, personalized response back to our user. This part here on the right side, where we actually extract the information from the knowledge base, this part is called semantic search, and we're going to now explore this concept in a little bit more detail. What is it and how it works? So semantic search, in contrast to the keyword search, does not search for the keywords, because we all know if we search for the keywords, sometimes the meaning gets kind of lost. So instead, semantic search allows for the search that actually takes the context of the text into account. So for example, if we see the context here, so this image that we see does not really talk about rule being a rule and rock being a rock, but it actually is a conversation about mutual appreciation between these two. So semantic search could actually capture this kind of meaning from the content and not just focus solely on the words themselves. So let's see first how the first step of retrieval augmented generation looks like. So how do we create this knowledge base that allows us the search? So as I mentioned, we start with a bunch of documents. And in order to allow the search, we have to represent the documents with the vectors in the vector space. So how do we do that? Because these vectors should somehow encode the context and the meaning of the documents into the vectors. So how do we do that? We actually use large language models. These are called embedding models, and they are they are encoder-based models. And these models are actually smart enough to represent the text in the vector space in a way that's very smart, actually. So let me move on to this image. For example, what we see here is that the vector, the point that says banana, so this is the vector in the vector space that represents the text about banana, is actually very similar to the vector that represents the text about the apple. So we see that similar content, semantically similar content, is actually encoded in a way that vectors representing similar text are actually also very close to the in the vector space. So for example, we see banana and apple are very close, but as opposed to a group of points representing the animals, which are also very close together, but they are at the same time, they are far away from fruit, because the meaning is semantically totally different. So because we are able to leverage to leverage large language models to encode our text in this smart way, then it's very easy to search for. Because if we want to search something that's close to our text that talks about bananas, we go into the vector space, we search for that vector that represents our banana text, and we actually search for the vectors that are close to banana, and the vectors that are in proximity actually represent the other text, say in our knowledge base, that speaks about something similar to bananas. So once we have encoded our text into our vector space, we normally store this vector data somewhere, and the most appropriate storage for that is these are vector databases. So why using vector databases? Because they are optimized to perform this kind of approximate nearest neighbor search, or they also have some other algorithms implemented. And we see here in the image that we have quite a few logos here. So the landscape of vector databases is actually quite broad already. So we have all sorts of vector databases. They are SQL-based, no SQL. They have different properties. Some are really fast. Some store the text as well. Some have role-based access control, which is a very desired property, and so on. So the field here is really kind of expanding. So this was about how do we create a knowledge base. And now let's see how we search in the knowledge base. So this is very similar that I've shown in the image before. So we have this user, and user asks a question, wants to know something. And we take the user query. We use the same embedding models to embed this query in the vector data, in the vector space. And then we go into our knowledge base and search for similar information. And basically, we return back to the user the documents that represents vectors that are very close in our knowledge base to the user query. Luckily, we don't always have to do that by ourselves, because we've seen on the previous presentation, our colleague explained very well how Google is doing. OpenAI also announced very recently that it will provide this kind of functionality out of the box. So we don't necessarily have to do that all by ourselves. So with that, we conclude the topic of retrieval augmented generation, and I give my word to my colleague Teja.
Thank you, Spela. So now let's imagine to go a step further. So what if we wanted, in addition to retrieve the information, we would also want to, search the information on the internet, call the APIs, or even execute the commands. Then we would actually come to another concept, which is the concept of AI agents, which are essentially orchestration tools that utilize GPT LLMs. And they're actually able, firstly, again, as before, to take the input from the user, take that input, and based on the input, to decide autonomously which action to execute. So that said, let's come to the next concept, which is function calling, which are actually the essence of GPT models in AI agents. They're actually, this function calling capability is actually, we can integrate function calling capability into the chat completion endpoint, and we can implement it in a way as we see it on this snippet on the right side. So we put it name, description, and parameter. And based on these descriptions, then the model is actually able, the LLM model is able to understand when and how and with what parameters the function is called. Okay, so let's now see that snippet on the slide. We see how to implement or to program or define our AI agent. This is the implementation of Llama Index, we see that this AI agent is able to do 6 things, or no, 5. Yeah, so it's able to retrieve the news summary, to make a purchase, to send an email, and basically when the user gives a query, the AI agent is able to decide autonomously which of these functions to call. So let us now go back to the concept of a RAG that Spela presented. So we have a user on the one side, and on the other side we have the AI agent. And then based on the user query, the AI agent is actually able to decide where to retrieve the information from. So from the knowledge base, from the web, or from some, I don't know, maybe SQL queries. Okay, so Spela, are you going to do that? Yeah. Now we are going to show you a demo that we programmed last week. But firstly, let's talk about that. We have a customer that is interested or maybe eager to travel, but he's not or she's not interested only in sightseeing, but also in music festivals and carnivals, for instance, as we are, to be honest. And the thing is that on the other side, we have a traveling agency that has this super smart chatbot. And here we are going to firstly to see what kind of data does that traveling agency have. So first of all, we have descriptions of various travel destinations. And this data is kept in unstructured sense. We see text documents with different destinations, each of them containing some sightseeing, and at the end also some information about the music festivals or carnivals, as we mentioned. And then the second, and then the second data source is about world carnivals. This, here we are seeing actually a screenshot of SQL database representing countries, cities, coordinates, population, and whether there is a carnival taking place or not, and the number of visitors at that festival, carnival actually. So we are seeing now structured data. And thirdly, we have real-time weather API that needs that takes as an input longitude and latitude of the city that we are interested in, and as an output we are given current weather. So let us now see the famous demo. So this is the user interface, and we want to travel to Serbia, and we're wondering what kind of sightseeing sites we would be able to see. And here we see that this text is actually very much similar to the first text file that we saw at the beginning, so from the first data set. And now we also want to know what kind of weather is in Belgrade, but we filmed that a few days ago, so I think the weather was clear. But actually, yeah, it was real-time weather information. Okay, so let's now see how it works. This is actually the real snippet from our code, our AI agent, and here are the functions that it's able to call. And the first one, get destination, is able to call and retrieve the data from the first data source. The second one is retrieving the data from the SQL database. And the last one, get weather, gets the real-time weather data through the API. Okay, so this here we are seeing slightly uglier user interface because we want to see how it works. It's actually terminal. And OK, we asked that agent again that we're traveling to Belgrade, and whether there are any sightseeing sites that one can see. And here the agent is reasoning, and firstly it goes to the get destination function that I mentioned before. So it goes and search for to the first data source, to the text files. And then that output is given to the LLM, and then the LLM produces that nice result. But let us not just stay here. Let's see something else. So we want to know what's the biggest carnival in the world in terms of number of visitors, and what's the weather there, and whether there are any sightseeings one can do there. And again, the agent is going to reason. Yeah, we call it like that. And as we see, it called the Carnival search tool. So it went to check into the SQL database for the answer to retrieve the information about the largest carnival. And also, it was smart enough to also know to retrieve the coordinates that it needs, because it's going to need that coordinates in order to retrieve the current weather from Rio de Janeiro in that case. And here on, I don't have yeah, I have that. And here we see that this was the first step, and then in the second step, it actually calls the get current weather function. So it calls the API, and here is the output of the API. And then thirdly, it also calls the function get destinations, and then it goes to search in the first data source. So what we're seeing here now is actually kind of chaining the steps one after another one, and lastly, providing all this information that it retrieved to the LLM again, and then it produces that nice result about the weather, and some information about Rio de Janeiro.
So the interesting thing here is that agent is actually able to reason for itself which functions to call, when to call them, in what order. It's also able to chain them. So for example, the output from one function is used as an input to the other function, and basically combine all these calls together. And this is something that the agent does completely autonomously, based on the functions and their descriptions that we provide them. With that, we conclude our presentation. So if there are any questions.
For some questions.
Yes.
Okay, do we have some questions already?
Yes, we do.
Sorry, here. Microphone, please.
Thank you very much for the presentation and for the demo. What are you using for similarity measure? Cosine similarity or something else?
Yes, yes. So there are a couple of measures we use. I think the cosine similarity is something that's widely used, so yes. Thank you.
Any other? Here. Here. Yes, you say.
Hi, thanks for this presentation. I was just wondering, have you already developed some kind of best practices in terms of testing this system when it's handling interactions with users? Because there might be certain edge cases where maybe this does not work. So like, have you thought about that? And if yes, have you found any solution to that yet?
Yes, actually, we have explored this space. So we see that some solutions are emerging. So what we have found to be kind of, that we thought that it's kind of the most suitable for our purpose, it's a tool, it's an open source tool, it's called PromptFoo. And it's actually, so it provides, it's not a debugger tool, it's more like for end-to-end testing. So you basically provide the agent with some scenario, let's say the history of conversation or just a single prompt, and then you actually say, this is the result that I am expecting, and the tool is able to provide some sort of measure. So either this could be like to compute the similarity between the actual and expected results, or maybe to compute, to find if certain text is contained in the answer and so on. So PromptFoo is the tool that we have personally discovered. But I mean, I would expect that this field will start to evolve very soon. I think that she had a question
Here,
as well.
yes, here.
Thank you for presentation. I have one question regarding type of vector database you use, and which is the most performant in your side.
Yeah, so we did do some research. So we have quite a wide space of vector databases. So for example, what we've discovered that's very interesting, that most of those databases do not have role-based access control, which was something that we required. So basically we found, for example, PostgreSQL, which has this PG vector extension that uses this. So we also have Redis, for example, that allows this feature, or Milvus, or also Elasticsearch. So because it was more simple for us, we used Postgres because we had it, we used it already in the project, but actually Postgres is not a very performant one. So according to the reviews, the one with best performance seems to be Kudrant, based on the research that we conducted. Thank you. I think we have another question over there.
Can I see? Ah, yeah, there's a hand there.
Thank you for the presentation. I just wanted clarification about the functions that you use. Do you define these functions yourselves? And what are the limits and the challenges you think, when defining these functions?
So, for example, something that we did very recently was something that surprised me really a lot. So basically, we're using this llama index library, which is very simple. So basically, you define a normal Python function, and basically, this is a wrapper of your functionality that you want to provide. And it works very simple. You define the function, you provide the types with simple Python typing. You provide description in the dot string, and llama index is able to parse this in a way that's required by the OpenAI endpoint. And basically, so we've discovered, I mean, it doesn't work perfectly. So there is some space for the error. But what was very interesting for us, for example, we had an example that we had to actually provide like a guided conversation. So the user was actually guided through the journey where the user had to provide different information at each step. So this is actually very opposite of something that we normally do. So normally user asks the question and the system provides the answer. So we had the opposite situation where the chatbot had to ask questions. So for example, we've done this with the AI agents. We provided the tool and the descriptions for each step of the function. So basically, these tools have called some backend API systems. Actually, it turned out that it works really surprisingly well. So just by adding the tools to the agent, the chatbot already knew what kind of journey does it have to guide the user through. So so far, I mean, the results so far are, at least to me, very amazing. I was surprised that it works so well. But there is a difference between ChatGPT, so GPT 3.5, and GPT-4. So I suggest to use 4, because there is quite a huge difference between them.
Thank
Another
you.
one. I think we have the time just for just one. Yeah. Just microphone, please. Here it comes.
Yeah, I was wondering whether you use some framework like LangChain, or did you develop something by yourself?
So I don't want to do any misconduct to LangChain, but that was our personal experience, and I've heard from someone else that had the similar experience. We started to use LangChain. It turned out that it had some bugs, which is not something that's, I mean, the bugs can be fixed. But in our experience, when they fixed the bugs, the changes were incompatible to the previous version. So we had to all the time kind of change our code and adapt it to the code that's been changed in LangChain. But this is a disclaimer. This was done over a year ago. So I would expect that also LangChain became more mature in this sense. So this is not in any way kind of disadvertising LangChain, but I just share my experience. So this is why we actually switched to Llama Index and continue to use this.
Okay, I will help to stop this here. Thank you. I will present you with the certificates, Spela and Tea, and thank you for this presentation.
Thank you.